Hello everyone. This is going to be a new course that would be on stochastic processes. Actually, you could say the entire course is going to be dedicated to random walks, but if I title it random walks, then maybe people would not necessarily search for that because it usually comes across the title as stochastic processes. Just a quick disclaimer, there's not going to be any math in this lecture. In this lecture, I'm just going to go over the description of the course, what the course is about, give you some history and that kind of information before we actually start doing the math. So if you want to see the math, just wait until lecture 2. That's when we will start with the actual math. This is also called Graduate Probability Part 2. So that, of course, raises questions. What is probability theory 1? And do you need to know that? So that's, maybe we should talk about that first. So there is undergraduate probability theory. Actually, you might wonder, so what should you know? So all you need, so this is a graduate course, but you can take it as an undergraduate. So the most important thing is mathematical maturity. And that means the ability to write a mathematical proof, to read a mathematical proof, to be able to look up something in the book, understand it yourself. That's the most important thing. And you also want a little bit of what we call advanced calculus. Basically, this means being able to write delta epsilon proofs. And you want to be comfortable with the real number line. If you know that, then you're pretty much set. So interestingly, you do not need to know Graduate Probability Part 1. So let's go over this. So we have undergraduate probability. So what do you do in that course? So that course, this is mostly computations, and you probably also do some applications. There's no emphasis on theory. So you learn what a random variable is, and then you learn how to do various computations involving random variables, and then you learn different types of random variables, different types what they call distributions, and then you see some of the applications in which it can be used. So if you want an analogy, this is sort of like calculus, where you're just learning how to do it. And then when you have graduate probability Part 1, this one is dedicated to the theory, the actual theory, right? The rigorous theory of probability. And this is very similar to what you call advanced calculus, where you focus on proofs. And it's possible to learn advanced calculus without knowing calculus, though that's a little bit silly, but it is possible. You do not really need that. However, to do graduate probability, because you already have the mathematical maturity, it becomes a bit easier to kind of jump straight into graduate probability 1 without knowing much about undergraduate probability. It's just that in graduate probability, you're not really focused so much on the applications, and you're not doing that many computations. It is expected that because you are a graduate student, if you have to do a computation, you'll be able to figure out yourself what you need to do. So that's what graduate probability 1 is about. And if you're curious to know what kind of topics make up that course, so the topics include, I would say, like if I was teaching graduate probability 1, we would talk about sample spaces, and then one talks about these things called probability measures on sample spaces. Then there's a discussion on random variables. You rigorously define what a random variable is. A distribution of a random variable, you define that. One talks about expectation and properties of expectation. And then once you have all of that, one would normally finish with some what you call limit theorems. There's actually a lot of limit theorems, so it would not be possible to do all of them, but at the very least, you would probably learn about the law of large numbers and the central limit theorem, maybe at least that. So that is what would, for the most part, make up a course in graduate probability part 1, where you're interested in the foundations of the subject. And actually, this is quite interesting. The foundations of probability theory, they involve, as you can see right over here, measures, as in measure theory. And measure theory is also used very much in real analysis. So when you take a graduate course in real analysis, you learn about measures. So it's pretty interesting, the connection that one has. Even though you are doing very different things, there's this unifying language for both of them. And what is graduate probability part 2? So it seems like you need to know this before you get to graduate probability 2. So graduate probability 2, and of course there's no like official title to this, but this is normally what people would do. Part 2. This is at least what we're going to do. This is going to be the study of what are known as stochastic processes. And the word stochastic in Greek means random. So you can also call it the study of random processes. So what's the difference between a random process and a random variable? Well, a random variable is when you just have one. If you do not know what a random variable is, that is okay. We will define it rigorously. But basically, it's a quantity that's random, right? You throw a dice. There's 6 possible numbers you can have. You call that a random variable. There's a random outcome that occurs, and each time you do it, you get something different. So when you first start working in probability theory, you focus a lot on random variables, and you just have one. Okay, and even when you do the limit theorems, when you have, let's say, a sequence of random variables like x1, x2, and so on, x3, you have a sequence. If you've ever seen, let's say, the central limit theorem, you assume that all of these are independent of each other, something we will define, and they all follow the same distribution. So in essence, you only have one random variable because they're all essentially the same to each other. So probability theory part 1 is very static. You just have one random variable. Maybe you have two, but you just have one. Even when you have a sequence of them, you just have one. Whereas in stochastic processes, you have a sequence of random variables. We often start our sequence at 0. Kind of think of this as the initial time. And you think of this as time. When n is 0, this is x0. This is sort of the way you begin. And then this is an evolving sequence of random variables. And for the most part, we usually never assume that they're independent of each other. And as the sequence evolves, it can become rather complicated. So probability theory part 2, this is a lot more dynamic because things are moving. So an example would be, and this would be the main source of examples that we will focus on, and this is what we call random walks. And what this is that you start, let's say, at the origin, and then you either add 1 or you add -1 using a coin toss. So x0 will start at 0. So technically, you can say that x0 is not random. It's always equal to 0. But the technical term is we say it's a constant random variable. It's a random variable, but it's always equal to 0. I know there's confusion here. What exactly then do we mean by random? But we'll get to that. That's what we have to define. So we start at 0, and then the next one is we will then move from 0 to the right or to the left with a coin toss. So let's say we end up at 1. Okay, so then the next one, so then we're located at 1. So then the next one, we do another coin toss, and we see where we end up. So we can go to the left, or we can go to the right again. And if we add 1 again, then now we're here. And you can see that this sequence of random variables now is dependent on the previous ones. So for example, x2, even though I might not know where I am on x2, if I'm currently located at 1, I can either go to 2 or I can go back to 0, but there's no way I can return back to -1 because the rule of the game is that you just make a single step. So you can see that if I know the value of x1, I know I do not necessarily know the value of x2, but I know that x2 cannot be all the way out there. So there is dependency. There is some information that you have based on where you're located. And this is going to be the primary source of our examples. This is technically, I should say, this is what we call a symmetric random walk, because it's 50-50 which way you go. You can have a random walk which is more favored to go to one side than the other, but we're not really going to focus on that as much. It's not as important. This is what we call a symmetric random walk. Okay, and let me tell you the course outline. So we're going to be learning stochastic processes. So random variables, a sequence of random variables, and for the most part, these will be random walks. And there's many things you can say about random walks, and they also appear in many different ways. So that's why this will be our primary source of examples. So this is going to be the outline of the course. So the outline of the course is we're going to start with a quick review of graduate probability part 1. And we're going to omit generalities and technical details. This will allow us to do a quick review of probability part 1. Normally, probability theory part 1 occupies an entire semester. We're going to do this in several classes. The goal is we'll be finished with probability theory part 1 in just 4 classes. And we're going to omit generalities because since the primary source of our examples are going to be random walks, it makes sense that all of the definitions that we give should be sufficient to discuss what we want to discuss. There's no need for us to be as general as possible if we're not going to be using that. And then we will also omit some technical proofs and technical definitions, but it will be done in a psychologically satisfying way. So I'll give you an example. We will rigorously define what a random variable is. So we normally denote a random variable by a capital X or a capital Y. That's the notation that people use. And when you have a random variable associated with a random variable, there's a very important number, which we call the expectation of a random variable, assuming it exists. It does not have to exist. So we will give the definition, or, well, we will give, so this is the part. Defining this rigorously in extreme generality is quite tedious. That's what takes a lot of effort. Defining it in simple examples will make sense, but defining it in the most general possible situation is going to be harder. And if you omit generalities, it becomes easier to define. And so I will show you the way you can define it, give you an idea of how to define it, but then there's going to be certain technical proofs associated with expectation. So for example, one of the properties of expectation is that if you take the expectation of a sum of 2 random variables, you will get the expectation of their sum. That would be like one of the properties. And the thing is, you prove this in graduate probability part 1, and we're not going to prove something like this. I mean, that's what we call a technical proof. You have to go back to the definitions, and the definitions are rather technical. But I think in the end, it's fairly believable. It's something that does not really bother you. It's not like I'm giving you a fact that is very counterintuitive, it's hard to understand, and then you just sort of have to accept it to go along with it. It's more going to be mostly the kind of facts that are very easily believable, and then you see where the complications lie in the definitions. And those complications and the technicalities are more appropriate for a probability theory part 1 course. So because of this, we'll be able to do probability part 2 with having a very minimal background. I'm going to develop the minimal background for doing probability theory part 1. I like to use the analogy that if you're like the example I like to use is the distinction between point set topology versus what we call algebraic topology. Normally, people learn this first and then they learn this second. However, that's not required. You can skip all of point set topology and immediately jump into algebraic topology. You will probably need just a few definitions from here, but once you just get enough definitions from here, you can just immediately start doing algebraic topology. So this is sort of the same thing. Normally, when people think of topology part 1, they think of point set topology, but you do not really need to do that if you're going to be doing topology 2. So it's the same idea. It's always a question of how you develop the material. If you do it in a way so that the definitions are adapted to what you want, you do not need the extreme generality from the previous course. So we're going to do a review of probability theory part 1, and then after that, we're going to we're going to spend a lot of time working with random walks, their properties, and theorems about them. There's a lot of theorems about them, a lot of very interesting theorems about them, and that will take up a big part of the class. After that, we're going to move into something called, so the plan is to move into Markov chains, which is a generalization of a random walk. And we're going to, of course, do the same thing. It's going to be properties plus theorems. And in fact, we'll actually do this. We'll do some applications. I'm going to show you why random walks are important in applications. And the applications, this is going to be this is going to be coded. So we're going to code some stuff on a computer, and you will appreciate how Markov chains are used in, are used in the actual world. They are important in various simulations that take place in the actual world. And I show you what properties that they have that make them important. So we're going to then move to Markov chains. And then after that, the goal would be we want to reach something called Brownian motion. So the distinction will lie in that when you work with random walks and Markov chains, you have basically time. You think of this as time, and it's indexed discretely. When you get to Brownian motion, whatever that is, we have to define that. You will have random variables that are indexed by a real parameter. So for every moment in time, something is happening. And Brownian motion, as you will see, is actually a continuous version of a random walk. That's what it would be. So this will be the motivation for setting up what this is. So the difficulty here is we would have to define it rigorously and show that it exists. And then we do something similar, discuss the properties, various theorems associated with that. And once you have Brownian motion, you can then, I guess, move into something called graduate probability part 3, when one can talk about stochastic differential equations and things like that, right? So you just keep on learning and learning and learning, and it never stops. Let me give you a history of this subject. Here's some history. So the history is, if you go back to the 1600s, and interestingly, this is not the type of history that goes back to ancient Greece. Usually, anytime we talk about math, we go back to ancient Greece, but not this time. In the 1600s, there were two people that you all know, Fermat and Pascal. They worked out many gambling problems. At that time, people would like to gamble, and they had all sorts of games involving cards, dice, roulettes, coins, and they had different rules. So naturally, one might wonder which of those games is more favorable and less favorable. Are any of those games actually fair? What does it mean to be fair? And all that stuff. So there's math that goes into that. And Fermat and Pascal, they thought about that, and they worked out a lot of the math, which is fairly elementary, but this is often what one does in an introductory undergraduate course in probability theory. You kind of start with gambling problems because that's the history of the subject. And this is kind of the way probability theory begins. It's not, it's not too serious. It's just for gambling. And then in the 1700s, there was Gauss and Laplace. Probably maybe add a few other people. And they were interested in, we can call this measurement of experimental error. So whenever you do a laboratory experiment and you measure something, so let's say you have very sensitive equipment and you put it on a scale, and the scale is set on micrograms. So let's say you get 12.3 micrograms as your first measurement, then you get 12.7, 13.1, 11.8. So you take 4 measurements, you try to do it as accurately as you can, but you're getting different numbers. And the reason why you're getting different numbers, we call this experimental error, measurement of experimental error, is that's not too surprising, because when it's very sensitive equipment, anything in the background can mess it up. So if a particle was to land on your equipment, that might mess it up. If you were to breathe on your equipment, it might mess it up. Maybe the air pressure in the room might mess it up. So there's all sorts of things that might mess it up. And maybe the equipment itself might not be perfect. It might be a little bit flawed. If you're using, let's say, a digital scale, it has to, if you have those scales for grams, it only measures it up to, let's say, 1 decimal point. And if it's in between, it just sort of has to decide whether to round up or round down. So whatever the reasons might be, you have measurement errors. And so what do you do here? Well, the natural thing you would do is you would just take the numbers and you would just take their average. But the thing is that we do not actually expect that the average would give us the correct answer. So the idea was, and this is how it's related to probability theory, is that somewhere on the number line you have the true value, and then you have your observations. Sometimes they can overestimate, sometimes they can underestimate, sometimes you can have like an outlier, as you call it, but you have to include that, you have to include all of them. And you have these measurements, and then you take the average of the measurements and you end up somewhere. Okay, so let's say this is the true value, and when you take the average of the measurements, maybe you end up over here. This is sort of maybe the average of all the measurements. And we do not actually expect that the average of the measurements will land on the true value. But how confident are we that we're somewhat close to the true value? And what does it have to do with? So Gauss, Laplace, and other people, they thought about this problem because this is a very natural problem that comes up when you're doing science. And this, in a way, it's like a probability problem, that anytime you have experimental error, it's sort of like a coin toss. It's not the best analogy, because a coin toss will either increase by a constant amount to the right or a constant amount to the left, like a random walk. This one is a little bit more difficult, but the idea was that you have your true value, right? So the idea is you have your true value, which is mysterious, we do not know, and then we add to it x1. So x1 is anything in the background that can affect the result of the experiment. It might either overestimate or underestimate the true value. It's a very small number. Maybe that number is like plus or minus 0.01. But then you have another error that might mess you up. So instead of maybe air pressure in the room making you overestimate or underestimate, maybe there's something else that's causing the fluctuation. Maybe a particle would land, and then that would be plus or minus 0.01. And then you have something else that messes up your measurements and so on. And what you get to see is that if you accumulate all of the errors, these are like the accumulated errors. So these are all of the things that can possibly go wrong and mess up your perfect measurement. If you accumulate them, this is sort of like a random walk, where you're adding up coin tosses. And on average, you're supposed to be around 0. So if you have a lot of them, so you should be around 0. But there is some fluctuations that might take place. And what Gauss and Laplace, they worked on this, and that led, and we will see this actually in the course, we'll do this very rigorously, that it led to what is known as the normal distribution. That's where the normal distribution came from. And it, as you can see, it's actually related to random walks. So the basic answer, this is sort of like the kind of answer they give you in a statistics 101 course. If you're a math major, you typically never take a statistics course. That's considered to be a totally different subject. It does use numbers, but so does accounting. Accounting uses numbers. It does not make it math. You take a statistics course. So your very first statistics course, they teach you something like that. So basically what it has to do with, if you're wondering, it has to do with the average of the numbers that you get. You have to consider the spread of the numbers. The more spread out the numbers are, the less confident you are in your estimate. This is what is also known as the variance. And how many samples you take. The more samples you take, the more accurate, the more confident you can be in the estimate that you make. So if you happen to know these three pieces of information, you can quantify. So once you take the average, right, you end up taking the average, but the spread and the number of samples that you take will create what is known as, they call, a confidence interval. You will build an interval around the average, and it's the question about whether or not the true value falls into that confidence interval, what you think, where you think it lies. So this is the way it's typically done, and as you can see, it involves a problem in probability theory. And this continued. That was not the only thing that Laplace done. He done other things as well, but this continued. And you can push this to the 1800s. You can say that you want to do the analysis, the analysis of controlled experiments. So that would mean is that you have two groups. You have a test group, and then you have a control group. Often given a placebo, and you want to see if some kind of treatment actually works. So you take people and you randomly assign them into one of two groups. So let's say you have 50 subjects in the test group and 50 subjects in the control group, and then you record the observations that you see, and you will always get different numbers. Even if the two groups are completely identical, you will always get different averages because of randomness. But the question is whether or not the numbers that you get are significant enough that it suggests that maybe the control group had an effect. So like, for example, you talk about some kind of drug that helps someone fall asleep. So some people will fall asleep faster, some people will fall asleep slower. You take the average of the two groups. There's going to be, it's a smaller number than the control group. Is that enough of a difference to suggest that this was a genuine difference, or was this just randomness? Or is it just the result of randomness? Is the difference large enough that it's probably not the result of randomness? So these are the kind of questions that comes up. And Laplace also looked into that as well. But Laplace lived in his work extends into the 1800s. And that's what people were doing. You were using probability theory here as well. Actually, if you're interested in this, this was also called inverse probability theory, because you're thinking backwards. In probability theory, if you have a probabilistic model, it will tell you what you expect to get. Here, you have the data, you do the experiments, you have the data, and then you try to go backwards. You try to say, well, what is the most likely probability model that led to that data? Nowadays, we call that statistics, but in the old days, that was called inverse probability theory. And I think Laplace was one of the people who coined this phrase, inverse probability theory. And the interesting thing about this is that all of this was not rigorous. Maybe to add something here, in the year 1900, maybe we can add this as well. In the year 1900, there was a person called Louis, and I'm probably going to mispronounce his name, Bachelor, who written a thesis. His math thesis was on the random motion of stock prices. So he written that in the year 1900. Of course, people before Bachelor all realized that stock prices, here it was in France, but people realized that stock prices, they randomly fluctuate up and down. So of course it's natural to consider coin tosses, but it's one thing to realize that. It's a totally different thing to actually come up with the necessarily math, the required math that enables you to talk about that more carefully. And this is also interesting that his advisor, so when you get your PhD, you usually have an advisor who works with you, and his advisor was Poincaré. Now, you might be surprised by that because Poincaré is a very popular name on this channel. We just completed 2 separate courses on topology, and Poincaré's name comes up everywhere, and it's interesting to see that he was also an advisor for someone working on stock prices. So you would not expect that, but Poincaré really did everything. And all of this, including 1900, all of this was not rigorous. You did not have a rigorous foundation for probability theory, just like you did not have a rigorous foundation for calculus. People had a good intuition for what they're doing, and they were able to rely on that intuition to say a lot of correct things. But of course, there was this question about what exactly do we mean by a random variable? How does one carefully define a random variable and all of that? And then how do you rigorously prove all of the theorems that we often use in probability theory? So the foundations were developed in the 1930s. So in the 1930s, there was a mathematician, Andrei Kolmogorov, who developed the foundations of probability theory. And the foundations, as we already said, they use measure theory, which is quite interesting. And since this time, when people learn probability theory in a more serious way, they always start with the foundations first. And that's what we're going to do. We're going to start with the foundations first. Now, this actually brings up a very interesting distinction that causes confusion. I tell this to my students all the time, but this is a good opportunity to mention this. A lot of people think that there's like 2 competing schools of math called pure math and applied math, right? This is what a lot of people think. But this is not true. That there's just math. Like, people think that applied math is when you take the math and you use it to solve a problem in the real world, but that's not math anymore. If you're building a bridge, you're not interested in the math behind the bridge. You're interested in that you can build a bridge that actually stands. If you're trying to come up with an investment strategy for the stock market, and you're using a little bit of math to help you, you're not doing applied mathematics, you're doing finance. You're using math as a tool. You're not interested in the math itself. You're just using math as a tool. The only distinction between these two is, in pure mathematics, you take problems from math itself and you try to turn that into a theory. So for instance, topology is considered to be pure mathematics because the idea of the topology is, if you take a sphere and you take the surface of a cube, you want to treat these as the same object, even though they're different objects, because the idea in topology is you have rubber sheet geometry. This is made out of rubber material and you can move it around. Now that's the intuition, but how do you make that rigorous? How do you give a rigorous foundation for that? And when you try to figure out how to do that and then prove theorems as the result of that, we call that topology, and one would typically call that pure mathematics because you're kind of staying within the confines of the math world. Whereas applied mathematics is, you have the like the fluctuations in stock prices, and you have this kind of motion that goes like this, and then you want to come up with a rigorous mathematical language that explains that kind of behavior. But you see, if you open up a graduate book in applied mathematics, it feels identical to pure mathematics. It's just that when they set up their definitions are more suitable for the phenomenon you see in the real world. But the actual definitions, it's like everything. So you're going to see this when we talk about the foundations of probability theory. The idea here is we want to be able to rigorously define by what we mean by a random experiment more carefully. And as you will see, it's just like any other subject of math. You start with a set, and then on that set, you have additional properties. And once you have that, then from that point on, you have your theory, and then you work out your theory. It's going to be the exact same thing. It's just that your primary motivation might be something outside of mathematics. So it's not that unusual for people to do both, because there's not really a distinction between them. So I'm not a big fan of doing this, because if you look at Andrei Kolmogorov and you read about his biography, they would probably describe him as an applied mathematician. But when you look at the foundations of the subject, you would by no means say that he's an applied mathematician, because the reality is this sort of like an arbitrary distinction that I'm not a fan of. If you look at the people who won the Abel Prize, let's say you look at the most prestigious mathematical award, if you go on Wikipedia and you look up all of the mathematicians who won the Abel Prize, you will notice that half of them work in areas of mathematics that would typically be called pure math, and half of them work in areas of mathematics that one would typically call applied math. But if you actually look at their work, it looks just like any other mathematical work. So that's why you want to remove this distinction. If you want to learn about math seriously, you do not want to have that distinction. If something interests you, then you should learn that, and you will be often surprised about the connections that exist between different areas of math. So for instance, we've developed a lot of material on this channel already that has to do with topology, and we mentioned that the solution to the Poincare conjecture has something to do with the way PDEs behave on a manifold, right? This what one typically say is an area of applied mathematics, somehow it appears in topology, because in the end, everything is sort of interconnected with each other. So that's why it's not the most useful disambiguation to have between these two subjects. And maybe I should finish with just with this. So this is going to be a follow along course. And what I mean is that the video lecture will consist of problem sets. So not the first video lecture, of course, because there's no math here, but it will consist of problem sets. So if you, after you watch the video lecture, in the video description, you will see a PDF, and that PDF will contain problem sets. And then you can try doing the problem sets. You can do the problem sets before you move on to the next one. Previously, I gave problem sets to my students without posting them online, but now that we have a bit more followers, maybe some people in the audience would like to follow along in real time. So we're going to be posting problem sets if you want to try working them out. You do not have to do the problem sets. You can just watch through all of the video lectures, but that's not the best way to learn math. Maybe if you want to get like a casual understanding of mathematics, if you just want to just casually get an idea of what stochastic processes are about and some of their theorems and some of the things we talk about, then that's okay. But if you want to learn this in a more serious way so that you can get to use this later on yourself, then you should focus on problem sets. You will get a lot out of that. And work on the problem sets, type them out for yourself. When you type it out, you understand it so much better yourself. So this is the way the course is going to go. So we'll conclude here, and then from this point on, we will do the math.